With our integrated rate law examples, we're going to start with the most common example, which is where you are already given the graphs and sometimes also given the data. So here we have a reaction of hydrogen peroxide decomposing. We've got our balanced equation, we've got coefficients, but we remember rate laws aren't determined by coefficients, they're determined by data. This is also a good one because we've just got that one reactant. So that's when and where the integrated rate law becomes very easy. So we have graphed our concentration versus time. We ran it for quite a while there, an hour. We kept the temperature constant, all good things to be aware of. And then as we look at our graphs, we really have to look at the titles and our axes because they're not always going to be in the order we want them to be in. In an ideal scenario, they would graph concentration, then natural log, then molarity, because that's how we saw it and we learned it. But if we read our graphs, it's really easy to see that these two are curves and natural log is straight. To answer the question, which is the key here, is that because that natural log is straight, it's first order, there's no more justification to that. That has shown up on free response and it says justify or explain. That's all you're doing. We don't need to know why, how, when, or any of the math theory that goes along with that. Using data and the appropriate equation, solve for K. So because it's first order, we go to the natural log equation, the final natural log minus the initial natural log minus KT. And this is where we would need some data here, or we'd have to read our graph a little bit more precisely than we can. So I just plugged in some values, final minus initial. I chose any time that I wanted. For some reason, I picked that guy right there. I got a value for K. And then a key is going back to what we did before. This is first order. So rate equals the concentration of peroxide raised to the first power. So what does that unit need to be? So we still made a rate law. It just didn't ask us what the rate law was. The experiment's repeated, a new value of K is calculated, and it's given. And hopefully what's comfortable here is that it's in the ballpark of what we already got, and the units match up, so that's good. How long does it take to decompose to here? So we could say, well, I've got initial, final, K, solve for T. Or we might recognize that this is double that, or it's asking how long to cut it in half. What is the half-life? So we've got the 0.693 over our K gave us our answer right there. And if you did it this way, you would see this minus this, or excuse me, that value right there is the 0.693. And that's where it comes from anyways. So we've got our data and we've got a pretty good idea of when and how to use that. Here, reactant A decomposes when we've got some graphs. They lined them up just the way we wanted them. Concentration, natural log, and reciprocal. Because reciprocal is a straight line, this is second order. Because it's second order, the half-life changes as the reaction proceeds. So that's what we know. We don't know what it is. It actually, the amount of time to cut it in half the first time is longer. The half-life gets shorter on this than to cut it in half, then to cut it in half, then to cut it in half. But we don't need to know whether it's increasing or decreasing, just that it's not constant. What's the approximate value for K with units? So the K is the slope here. So we just need to find some data we're comfortable reading. I said, okay, 200 seconds, it hits right at the, what did I think that hit at? Why did I choose 50? Well, looks like I'm going to fix this one with a quick pause. And once again, you never saw the mistake, but I was just finding data I thought I could read, right? I come up 200 seconds. It's right here, equally between what would be the 20 and the 30 in terms of those values. So we've got that right there. And then we notice that it's not hitting 0, 0. At our time equal to 0, we still have a value of 5. So maybe not exact values, but without better data, hard to do any better than that. So we've got a slope. It matches our thing there. And then as second order, this kind of makes sense in a couple ways. We're looking at 1 over m, but we also think I've got molarity squared, I need to cancel one of those out. So some just examples here of how we can have first or second order, how the graphs can look different ways, how we can use the equations, or how we can look directly at the graph to get the information we need.